Hi, and welcome to the part 2 video on nuclear reactions. So you've already covered these topics. We're now going to start looking at some other things we need to know about nuclear reactions in addition to the particles and the atomic symbols. Let's take a look at the structure of a nuclear reaction equation. So in a nuclear reaction equation, we write on the left of the arrow the reactants. Those are the things we start off with. And on the right of the arrow, we write our products. Those are the things that we make. So in this reaction here, we're reacting nitrogen-14 and helium-4 together to make oxygen-17 and hydrogen-1. The nitrogen-4 and the nitrogen-14 and helium-4 are our reactants, and the oxygen-17 and the hydrogen-1 are our products. So before we go into sort of balancing nuclear reaction equations, which are super important, I want us to look at some examples and types of nuclear reactions, and then we can go back to the balancing. So there are several types of nuclear reactions. The first two we're going to look at, we're not going to spend too long on because you're going to see this more in the unit where we cover stars, because these are some of the reactions that occur in stars. But it's also important to mention them here, so that's why I'm pausing just to mention them. So the first two are fusion and fission. These are high energy reactions, and they're kind of opposite of one another. Fusion involves combining two or more, so please add that, or more, lighter nuclei into a heavier one. So let's take a look at this example. We have polonium-214 and helium-4, and these two are reacting together, so these are our two reactants, to make a larger single nucleus, radon-218. So what makes this fusion? We're starting with two or more things that combine to make one larger one. Fission is the opposite. So with a fission reaction, we are splitting a heavier nucleus, so something that's bigger, so we have a polonium-214, and we're splitting it into two or more, in this case three, smaller nuclei, gallium-80, krypton-90, and chlorine-42. Now you may look at this and say, it's for a fission reaction, shouldn't we only start with one nucleus? Well, we technically are, even though there's a neutron here. This neutron, we kind of ignore it in terms of figuring out if it's fission or not, because a neutron is not an element on the periodic table. We wouldn't find a neutron on our periodic table, okay? The neutron sort of acts like when you're playing pool and you use that first pool ball, the white pool ball, to split up the pool balls. That's what this neutron's doing. It's kind of helping to split this up. So that's fission and fusion. Now the ones I really want us to know, since we're in this unit we've been talking about radioactive decay, are radioactive decay reactions. So what are radioactive decay reactions? A radioactive decay reaction is a spontaneous, meaning it happens on its own, breakdown of a radioactive isotope, which is the parent isotope, to make a more stable daughter isotope. So again, it's a spontaneous, happens on its own, breakdown of a radioactive isotope, the parent isotope, to make a more stable daughter isotope. So if you need to, make sure you pause the video. Alright, so there are three types of decay reactions that you all need to know. Alpha decay, beta decay, and gamma decay. We already seen previously those symbols. So remember, here's an alpha particle. It's a helium-4 nucleus, where we can use the alpha symbol. Beta particle, which is an electron or a beta symbol, and a gamma, which is a photon of light, and that has that symbol, kind of looks like a Y. So these are the three particles that we're looking at, or decay reactions. So let's take a quick look at what a decay reaction looks like. If you look at these three decay reactions, you'll notice that they have some similarities. Let's start off to the left of the arrow. How many things do you see on the left? So in each case, you see only one reactant, one thing to the left of the arrow. Here's our arrow, and there's only one thing on to the left of it. So all decay reactions have one reactant. And then on the right, you have two things. Right of the arrow, you see there's two products. So in each decay reaction, we start off with a parent isotope that's unstable to break down to form a daughter isotope in one of the radioactive particles. For an alpha decay, the radioactive particle will be an alpha particle, which is a helium-4 nucleus. Beta, it will be an electron. And for gamma, it will be a gamma particle. Now, we can write these, instead of writing it as a, for example, for alpha decay, instead of writing it as an alpha helium-4 nucleus, we can also write it as an alpha particle. For the beta, we can write the electron as a beta particle, and for a gamma, we can write it as a gamma particle without any numbers on it. So how would I read these reactions? For the alpha reaction, I would read it as radium-226 breaks down to form radon-222 and an alpha particle or a helium-4 nucleus. For the beta decay, I read this as iodine-131 breaks down to form xenon-131 and a beta particle, which again is our high energy electron. And for the last one, for the gamma, I have radium-226 breaking down to form radium-226 and a gamma particle. But wait a second, it doesn't look like there has been any change. Well, there has been. You see that star there? What happens in a gamma decay, instead of it shooting out a particle like a beta or an alpha particle, it releases energy. So you can think of the radium with that star as having a lot of energy, like it's really, really hot. And when it undergoes gamma decay, it cools down to its daughter isotope and a gamma particle, which is a photon of light. All right, once you've done that, now it's time to do some more practice. So in this case for the practice, what we're going to focus on is, can you identify what type of reaction this is? Alpha, beta, gamma decay, or neither. So if it's not one of these three types of decays, you would write neither. So for example, in this first reaction, I see I have one reactant and I have two products. One of my products is a beta particle. So this is an indicator that this is a beta decay. Why? Because I have one reactant and two products, and one of the products is a beta. So we'll go ahead and take a moment to try the rest, and then again check your answers either in Schoology or with your teacher. I hope you found this video helpful. Have a quality day.